prove a specific kind of trigonometric identity, an identity for either cos n theta, sine n theta, or tan n theta in terms of essentially powers of cos theta, sine theta, and tan theta. And this is done by De Moivre's theorem. And what I'm going to do today is show you applications of these identities. And actually, what's really nice is the identities that we form can be used to solve certain polynomial equations via doing a trigonometric substitution. So example 1 is meant to be illustrative of the kind of thing you might get in an exam. In the first part, they ask you to use De Moivre's theorem to prove this identity for tan 5 theta. This is what we did in the last lesson. Can I recommend very strongly that you pause the video, you have a go at check, you can do that. I'll go through the answer in a second, and then we'll worry about part 2 of the question. So here is a solution via De Moivre's theorem. So cos 5 theta plus I sine 5 theta, let's get my highlighter pen on, is given by cos theta plus I sine theta to the power of 5. It is sensible to let C stand for cos theta and S for sine theta. So this is C plus IS to the 5, which expands in the following way by a binomial expansion. C to the 5 plus 5 choose 1, which is 5c to the 4 is, plus 5 choose 2, which is 10c cubed is all squared, plus 5 choose 3, which is 10c squared is all cubed, 5 choose 4, which is 5c is to the 4 plus is to the 5. If you then expand the brackets and simplify the powers of I, you get c to the 5 plus 5i c to the 4s. I squared is minus 1, so minus 10c cubed s squared. I cubed is minus I, so minus 10ic squared s cubed. I to the 4 is 1, so plus 5c to the 4, cs to the 4, plus I sine s to the 5, because I to the 5 is I. If you compare the real and imaginary parts, you will get cos 5 theta is the top expression, c to the 5 minus 10c cubed s squared plus 5c s to the 4. Sine to the 5 is the bottom expression, 5c to the 4s minus 10c squared s cubed plus c to the 5. Then to get expression for tan 5 theta, you want to divide one by the other, sine 5 theta over cos 5 theta. So there is my expression for sine 5 theta, which I've rewritten in terms of sines and coses. 5 cos to the 4 sine minus 10 cos squared sine cubed plus sine to the 5 divided by cos to the 5 is cos 5, is cos to the power 5 minus 10 sine cubed cos cubed sine squared plus 5 cos sine to the 4. If you divide the whole of the top and the whole of the bottom by cos to the power 5, and because this is a show that question, I think you've got to explain that you've done that or you're not going to get full credit. It simplifies to give you the required identity, and we are done. So this is what we know so far, and then part 2 is what I'm going to do is I'm going to use this to solve a quintic, a power 5 equation. So the equation I'm trying to solve is this. It's a horrible quintic power 5 equation. These are really difficult to solve. It's got surds in it as well. I'm going to solve this by using this trig identity to turn it into a simple trig equation. The trig equation I'm going to turn it into is tan 5 theta is root 3, and this is doing the substitution t is tan theta. So what I need to do is take the equation that we're given, rewrite it in a form where hopefully I can write it as that, because that's what tan 5 theta is equal to root 3. If I can show that that is root 3, then tan 5 theta is root 3. Now what I'm going to do is you can, if you want, replace t with tan theta straight away. But I'm going to do some rearrangement first of all, and then I'll replace t with tan theta in a minute. And the rearrangement I'm doing is really inspired by this. I'm going to make root 3 the subject of this equation. So you'll see at the moment you have got 6 terms. 3 of them have got root 3s and 3 of them haven't. I'll get the root 3 terms on one side. So therefore, this equation is the same as t to the 5 minus 10t cubed plus 5t is equal to 5 root 3 t to the 4 minus 10 root 3 t squared plus root 3. And that is the same as root 3 into, sorry, there should be a 4 there, 5t to the 4 minus 10t squared plus 1. So therefore, the equation is the same as t to the 5 minus 10t cubed plus 5t divided by 5t to the 4 minus 10t squared plus 1 is equal to root 3. But we're now going to replace t with tan theta. I'm going to change the order in which the terms are written on the top and the bottom. So the first time I'm going to write down is 5t, which is 5 tan theta. Minus 10t cubed is minus 10 tan cubed theta. Plus t to the 5 is tan 5 theta. All divided by, if you change the order again, you get 1 minus 10 tan squared theta plus 5 tan to the 4 theta. But that is my identity for tan 5 theta, so consequently I can say that my equation transforms into tan 5 theta is equal to root 3. So I started off with this horrible polynomial equation involving t. By letting t be tan theta, I've transformed it into this trig equation using the identity we previously solved. Tan 5 theta is root 3. So what I'm now going to do is solve this equation to get theta, and then I'm going to go back and work out t. Now, a little bit of mathematical common sense is required. This is a quintic equation. It's a power 5 equation. So consequently, we should expect that there will be 5 solutions for t. A quadratic has 2 solutions, a cubic has 3, a quartic has 4, a quintic has 5. This therefore means I need 5 solutions for theta. So if you inverse tan both sides, you get 5 theta is arctan or inverse tan of root 3. And it doesn't specify this, but I'm going to get the answers in radians, ladies and gentlemen, boys and girls. Okay, so if you do inverse tan of root 3, you may do that on your calculator. That will give me inverse tan of root 3 is pi over 3. So in a minute, I'll divide that by 5 to get a value for theta, and then that will give me 1 value for t. But I want 5 values for t, so I need 5 values of theta. So because the tan graph repeats every 180 degrees, which is pi radians, 5 theta could be that, or I could add on pi to that, and that will give me 4 pi over 3. Add on pi to that, and that will give me 7 pi over 3. Add on pi to that, and that will give me 10 pi over 3. Add on pi to that, and it will give me 13 pi over 3. And I'm stopping because I've got 5 values. I will come back in a minute and explain to you what happens if you carry on any further. So this gives me 5 values for 5 theta. Dividing through by 5, I therefore have theta can be pi over 15, 4 pi over 15, 7 pi over 15, 10 pi over 15, which actually simplifies to give 2 pi over 3, or 13 pi over 15. But I haven't finished yet because I wanted to solve the original equation, so my solutions need to be values of t. But t is tan theta. So the first value of t is tan of pi over 15. The second value of t is tan of 4 pi over 15, or it could be tan of 7 pi over 15, or it could be tan of 10 pi over 15, which is 2 pi over 3, or it could be tan of 13 pi over 15. So these are the 5 roots of the original equation. They are expressed as tans of angles. And that's what the question said. It said, hence solve the quintic equation, giving the roots in terms of tan. And just one minor little point, we're done with this question, to explain what you might be thinking is, well, what happened if you carried on further? If I'd carried on getting extra values of theta, the next one I would have got is 16 pi over 3. That would have given me theta is 16 pi over 15. That would have given me t is tan of 16 pi over 15. But tan of 16 pi over 15 and tan of pi over 15 are the same number. That's because they differ by pi radians. So whilst we could have got infinitely many values of theta, the values of t will repeat after you've got 5 distinct ones. Okay, folks, on the next video, I will do the second example from this question. This lesson.